Everyone has felt this. A playground swing, push at just the right moment, and almost no effort sends it soaring. Push a little too soon or too late, and it fights you. That everyday trick has a name: resonance. And the very same effect, hidden inside an electric circuit, is one of the most useful and most dangerous forces in all of electrical engineering. Handled well, it can send power through empty air. Handled badly, it can quietly tear a power grid apart. So, let us build it, properly, from the ground up. What it is, how it works, and why every engineer has to respect it. First, the picture in your head. On a swing, energy is never lost. It only changes form. At the bottom, the swing moves fastest. Pure motion. As it climbs, that motion trades away for height, until, at the very top, it stops for an instant. Pure height. Then, height pours back into motion, over and over. That trade has just one natural rhythm, set by the swing itself. And to make it grow, you do not push hard. You push in time. Small nudges, matched to that rhythm, add up, and the swing climbs from almost nothing. Match the rhythm, and little becomes large. That is resonance. Now let us find its electrical twin. Electricity has two ways to store energy, and they are perfect opposites. A capacitor stores it in an electric field, in still waiting charge. That is like the swing at the top, all height. An inductor, just a coil, stores it in a magnetic field, but only while current is moving. That is like the swing at the bottom, all motion. Wire these two into a single loop, and you have built an electrical swing. The capacitor is the height, the inductor is the motion. Now charge the capacitor and let go. It empties through the coil. Current builds, the magnetic field grows until the capacitor is flat and all the energy has moved into the coil. But the coil will not let the current simply stop. It pushes on and charges the capacitor the other way. Energy sloshes, electric to magnetic and back again, exactly like motion and height on the swing. Plot the voltage as this happens, and a smooth wave appears. An alternating current, ringing entirely on its own. And like the swing, this ringing has one natural frequency, set only by the parts. A larger capacitor holds more charge to move, so it rings more slowly. A larger inductor fights changes in current harder, so, again, more slowly. Put them together, and you get the resonant frequency. 1/2 pi times the root of L times C. Change L or C, and you retune that frequency, exactly as a longer or shorter swing changes its own rhythm. But why this exact frequency and no other? Here is the real heart of it. When you drive the circuit, both the coil and the capacitor push back against the current. We call that push reactance. The coil's reactance grows as frequency rises. The capacitor's reactance shrinks as frequency rises. So there is one frequency, and only one, where the two are equal, and because they are opposite in nature, at that point they completely cancel. Set the inductive reactance equal to the capacitive reactance, solve, and out falls the very same formula. Resonance is simply the frequency where the inductor and the capacitor erase each other. That canceling has dramatic consequences. In a series circuit, at resonance, the inductor and the capacitor wipe each other out, and only the small resistance is left. The circuit's opposition to current collapses to almost nothing. So the current shoots up, a sharp, towering peak, at exactly the resonant frequency. A tiny push at the right frequency now produces an enormous current. This is series resonance. Now, wire the same two parts side by side, in parallel, and you get the mirror image. At resonance, a large current sloshes around inside the loop, between the coil and the capacitor, while the circuit draws almost nothing from the source. To the outside world, it looks like an enormous resistance. It blocks that one frequency instead of passing it. So series resonance welcomes a frequency. Parallel resonance rejects it. Those two behaviors are the engineer's tools. And those tools are everywhere. Tune a resonant circuit to a single frequency, and it becomes a filter. It can pick one radio station out of the crowded air, or trap an unwanted harmonic before it spreads across a grid. Build two coils that resonate at the same frequency, and energy will leap across the gap between them with no wires at all. That is how your phone charges on a pad, and how an electric car can draw power straight from the road. All of it, resonance, put to work. But the same effect has a darker side. To improve power factor, utilities connect large capacitor banks to the grid. Those capacitors, together with the inductance of the transformers and lines, quietly form a resonant circuit that no one intended. If the grid then carries a harmonic near that hidden resonance, series resonance can drive currents sky high, or parallel resonance can push voltages far past safe limits. Insulation fails, capacitors burst, which is exactly why engineers calculate where these resonances lie and detune them long before they can do any harm. So that is resonance from the inside out. Two opposite stores of energy, trading back and forth with a single natural rhythm. Drive them at that rhythm, the one point where the inductor and the capacitor exactly cancel, and small becomes overwhelming. Master it, and you can tune a radio, clean up a grid, or send power across thin air. Ignore it, and it will find the weak spot in your system and break it. One formula holds the whole story, 1/2 pi, root LC. If this finally made electrical resonance click for you, I would genuinely love it if you liked the video, subscribed so you never miss the next one, and shared it with someone who would enjoy it too. Thank you so much for watching.